Let's get going with the Pythagorean theorem. The Pythagorean theorem deals with right triangles. Obviously, that figure that you see on your left there is a triangle, but right triangles are special. They have at least one 90-degree angle. By that we mean an angle where one side is like along the ground and the other side is straight up and down. We've all dealt with right triangles, and we label the triangles A, B, and C. Now, there are some specific names that we use when we deal with right triangles. We call the long side, the slanty side, if you have it set up this way, the hypotenuse. That's the long side of a right triangle. Then the other two sides are called the legs of the triangle. What the Pythagorean theorem asserts is that if we square the legs, we get the square of the hypotenuse if we add the square of the legs together. The way it's stated exactly mathematically is the square of the hypotenuse, the long side, is equal to the sum of the squares of the other two sides. I have to be careful when I say that. But what it's really saying is if you take the squares of the two shorter sides of the right triangle, add them together, you get the square of the hypotenuse. Let's take a look at how that might work. First of all, what we're saying is this. There are the two legs of the triangle. There is the hypotenuse. If we square those sides, what are we really talking about? We're actually talking about a square whose side is A in this case, or A squared. A square whose side is B, or B squared, and another square whose side is C, or C squared. And we're saying it's generally true that if one of those angles is a right triangle, the area of the two legs added together is the same as, is equal to, the area of the long side, the hypotenuse. C squared is equal to A squared plus B squared. Let's take this theorem and actually apply it to some cases in mathematics. Here's a really good problem to start with to apply the Pythagorean theorem. We have a right triangle with two legs, 3 feet and 4 feet. And again, when you indicate a right triangle, if you draw that little square where the right angle is, that will tell everyone that you're dealing with a right triangle. What we'd like to do is calculate C, the length of the hypotenuse. We substitute the lengths of the legs in for A and B, and then we need to square them. 3 times 3 is 9. Feet times feet is feet squared. So we have 9 square feet plus 16 square feet. The next thing we need to do is add those squares to get 25 square feet is equal to C squared. But we want C. So we need to take the square root of both sides. The square root of 25 square feet is 5 feet. The square root of C squared is just C. So we have the length of the hypotenuse is equal to 5. Notice that we have a very nice thing happen here. This is what's called in the business a 3-4-5 triangle. And it's one of those that work out nicely because 3 squared and 4 squared add to 25 squared, which gives you a perfect square, so to find the square root of that is easy. You hardly have to use your calculator. And in fact, carpenters use 3-4-5 triangles to make sure that when they're building something, they've gotten the corners correct. They measure off 4 feet on one side, 3 feet on the other, then measure the hypotenuse, and if they don't have 5 feet exactly, it tells them that that angle is off. So using the 3-4-5 triangle is a very useful thing in everyday life, actually. Let's look at another problem, though. Here's one that deals a little less with everyday life, but something you may be familiar with. A baseball diamond's really a square with the sides 90 feet. What's the distance from second base to home plate? Let's take a look at what we're given here. We're given that the baseball diamond's a square with sides of 90 feet, good to know. And what we want to know is what's the distance from second base to home plate. Let's draw the diagram. First we'll summarize the information. Here's the diagram of what the baseball diamond looks like. And if you look at it a little sideways, you see what you have is a square. We see here, in a way, what we have is a right triangle between any two of those 90s, and we want to know what the hypotenuse of that triangle is. We can just say A, B, C, and it's the same situation that we had before, and we need to use the Pythagorean theorem. The square of A plus the square of B is equal to the square of C. Let's apply this now. We know that A squared and B squared are going to both be 90 in this case. We have square of 90 plus the square of 90 equals C squared. The square of 90 is 8,100, 8,100, and then if I have to square the foot, I get foot squared. Then if I add those two together, I get C squared is equal to 16,200 feet squared, but I want C. Now, this is a little bit more difficult and, in fact, a case for your calculator. To take the square root of both sides, I get that C is equal to 127.26 feet, or we can just round that off and say that the distance between home plate and second base is awfully close to 127 feet. Let's look at another common use of the Pythagorean theorem in building and construction. I've already indicated one use for 3, 4, 5 triangles. Here's another, a calculation that often needs to be made. A contractor needs to build a roof for a house 50 feet across that's 10 feet high in the center. How long must each of the roof beams be to accomplish this? And they want us to find the answer to the nearest inch. This is the same as converting decimal time to minutes. Here we have to convert decimal feet back to inches, because in the system that most contractors use in this country, we're using feet and inches. Let's take a look at what we're given in the problem. The house is 50 feet across, and the attic is 10 feet high in the center, and what we want to know is how long must each of those roof beams be. Here's the summary of the information of what we're given and what's asked, and then here is a diagram that will help us to solve the problem. We see we have a symmetric situation here. The house is 50 feet across, and actually what we can do is say we have a right angle if we go halfway. So there's the 10 feet dropped from the very top of the attic down, and halfway across the 50 is 25. So we have now a right triangle with one leg 10 feet, the other leg 25 feet, and we're solving for the hypotenuse using the Pythagorean theorem, a squared plus b squared equals c squared. We plug in those numbers. C squared is 10 feet squared plus 25 feet squared. We do the math multiplying both of those numbers by themselves. We add it together. Then we take the square root of the 725 feet squared, using our calculator at this point. When we do that, we find that the length of the beam has to be 26.93 feet. But remember, we're not quite done yet. We need to convert 26.93 feet to feet and inches. So really what we need to do is convert 0.93 feet, which is less than 1 foot, but not much less. 0.93 is awful close to 1, so we know we're going to have quite a few inches in there. 0.93 feet is equivalent to how many inches? 1 foot is 12 inches, so if I multiply 12 by 0.93, I find out that's 11 and a little more inches. My final answer then is the length of the beam I need is 26 feet 11 inches. Now let's leave the Pythagorean theorem and look at the area of a triangle. We talked about the length of the sides before of a special triangle. Now we're looking at area. We've talked already about the area of a parallelogram being the height, not the length of the side, but the distance from the base, notice that 90-degree angle there, up. We can see that if the area of a parallelogram is the base times the height, and we draw a diagonal across from one extreme corner of the parallelogram to the other, what we have is a couple of triangles. So that it follows the area of a triangle has to be half the area of an equivalent parallelogram. The area of a triangle is 1/2 the base times the height. This is certainly a formula worth memorizing. That's a big hint. Let's look at doing some actual calculations with the area of triangles. Notice here we have that factor of 1/2. We have to think about how we're going to handle that. And in the most general sense, is how do we handle a fraction times a decimal? And one way is to handle that decimal just as if it was a fraction. The 6.28 is 6.28 over 1. I can just do the math. 3 times 6.28 divided by 5, which is really what that fraction says. Method 1 is just do it as a fraction and do the math as you would do fractional math. The second method is just to change 3/5 or whatever that fraction is to a decimal, and you know how to do that. In this case it's 0.6, and then we can just do a decimal multiplication. And there's no one way to do this. I always do whichever seems easiest at the particular time that I'm doing the problem. Let's actually calculate some areas now. Let's find the area of this triangle. We have an area whose base is 10.5 feet and whose height is 3.6 feet. The formula for the area is 1/2 the base times the height. We plug in, then we can continue to do the math. 10.5 times 3.6, I can do this calculation, is 37.80. And now I need to take 1/2 of that. The easiest way for these kinds of problems, as far as I'm concerned, is to say 1/2 is equivalent to 0.5 and then just do the math. The other way of doing it is 1/2 means dividing it by 2. In essence, you're doing it as a fraction, and in both cases you'll get the same result. It's 18.9. And either way you would like to do it works fine. Going back now to the finding the area, it's the 1/2 the base times the height. We put that in, and we have to remember now we're multiplying feet times feet, getting feet squared. We always have to express area in square measure, and the result is the area is 18.9 square feet. Let's do another one. Let's find this area. The triangle looks a little funny, but it works the same way. Area is 1/2 the base times the height. There's the base, the same as it was before, but now the height, you have to extend the base of the triangle a little bit and measure from that top corner down to the ground, 2.6 feet. Again, we just now do the multiplication. 6.3 times 2.6 is 16.38 square feet. We take 1/2 of that, either by multiplying by 0.5 or dividing by 2, however you like, and we get that the area is 8.19 square feet. or to round it off if you want to, it's 8.2 square feet. And typically, if your lengths are given to the nearest tenth, and when you multiply that, you get something to the nearest hundredth, it's not untypical to round off just to the length that you were given, in this case to the nearest tenth. Let's now just extend what we know about triangles to the area of trapezoids. Here's a trapezoid, and there are some other trapezoid, and that's a four-sided figure with one pair of parallel sides. In all three of the cases here, you see the parallel sides are the top and bottom, and then the other sides aren't exactly parallel to each other. You can see they're going to join somewhere. Let's look at the formula for the area. In this case, we have two parallel sides, A and B, and there's the height. The area of a trapezoid is 1/2 the height times the sum of those two parallel sides. It's 1/2 the height times the sum of the lengths of the parallel sides. Let's look at an example. We have 10.3 feet as one parallel side, 20.4 is the other, so that when we multiply this, the height is 6 feet, and then we have to add the 10.3 and 20.4, and we work this out exactly as we would the area of a triangle. The only difference now is that we need to add in those two parallel sides before we do the rest of the mathematics. Straightforward, and again, just a slightly different formula. Instead of the area of the height times 1/2 the height times the base as you would for a triangle, you now have to add the lengths of those two parallel sides. Let's move along now and look at something rather important, circular objects. When we deal with circles, there is a certain vocabulary we use that we all need to talk about. First of all, a circle is, well, you know what circles are. If you're at the center and you measure anywhere from the center to the edge of the circle, you always get the same distance. We call the distance across a circle that goes through the center the diameter, and we call the radius the distance from the center of the circle to the edge. So if you're going all the way across, you're dealing with the diameter. If you're going from the center to an edge, that's called a radius. We call the distance around a circle the circumference of the circle, the distance around it. There's a very interesting number. The number is called pi, and that's the ratio. It's the, if we take the circumference of the circle and divide by the diameter of the circle, and it doesn't matter how big or small the circle is, it turns out that that division always gives us the same number that's often approximated as a fraction as 22/7, and it's approximated as a decimal as 3.14. In fact, something interesting happens. That isn't exactly 3.14. Pi goes on in an infinite decimal sequence. I've seen pi rendered to 1,000,000 decimal places. And there are actually mnemonics for remembering how big the decimal places of pi. In fact, there are even poems about it. There once was a fellow from Greece who forgot pi's last decimal piece. So he used electronics to collect mnemonics, and now he's hooked, there is no release. What they're saying here with this little poem is that there are loads of ways of remembering pi to a bunch of different decimal places. Here are a few of them that I found. How I wish I could calculate pi. Notice the length of those words, 3141592. So the length of the words, how I wish I could calculate pi, gives you pi to 6 decimal places. Here's another one that goes even to more decimal places. Sir, I bear a rhyme excelling in mystic force and magic spelling. Celestial sprites elucidate my own striving can't relate, or locate those who can cogitate and so finally terminate. If you can remember that, you know pi to a lot of decimal places. Now let's take what we've learned about pi and apply it to a problem. Remember now, you can use pi to all the decimal places you want, but 3.14 is going to be good enough for us in this class. Here's the problem. We want to find the circumference and area of a circle having a radius of 8.4 feet. The circumference of a circle is going to be pi times the diameter, because remember, if we divide both sides by the diameter, that's our definition of pi. The ratio of the circumference to the diameter, or the circumference over the diameter. So the circumference then is pi times the diameter, but we know the diameter of a circle has got to be twice the radius, because the radius is the distance from the center to an edge, and you can see that the diameter is just 2 radii. The circumference is 2 pi r, or pi d. Another good formula to memorize. Get out your little practice cards. You're going to be expected to remember this. It's a very important formula in mathematics. We now just substitute the length, the radius for this, so we see that the circumference is 2 times 3.14 times 8.4. When I work this out, I find that the circumference is 52.752 feet. And again, since I'm given the radius to the nearest tenth, it's best to round it off to the equivalent nearest tenth. And so what we say is that the circumference, good enough for rock and roll, is 52.8 feet. That's the distance around that circle. If you had a circle 8.4 feet from the center to the edge and you walked around it, you would be walking 52.8 feet, the circumference of the circle. Now if we want to find the area, we hit another important formula, and a fairly simple one, and another one to write on your cards of things to memorize. The area of a circle is pi r squared, 3.14 and whatever else, times the square of the radius multiplied by itself. In this case, we would just do the calculation in a straightforward way, and remember that we need something squared. When you're dealing with an area, you're dealing with square units. It makes sense then that the radius is squared. The area is 3.14 times 8.4 times 8.4. If I do this, I find that multiplying 8.4 by 8.4, I get 70.56 on my trusty calculator. Multiplying that by pi, I find I have 221.5584, and of course the unit is square feet. Notice that again I round that to the nearest tenth of a decimal place, because that's what r is given in. You can actually say something wrong with your calculator, can lead you to answers which may not be incorrect, but they're somewhat misleading. If I say, for example, I know an area, the area of this circle, for example, is 221.5584 square feet. That implies that I've measured the radius very, very carefully. And so I can tell you that that's the answer absolutely, when in fact I've used kind of a crude ruler to measure that radius. I've measured it to 8.4 inches. So that says that I only know the radius. I'm using kind of a crude ruler. I've measured it poorly, to the nearest tenth of an inch. If I say I measured it, if I report the radius as 8.40, that implies that I've measured it carefully and I know it to the nearest hundredth of an inch. you need to be careful that your calculator doesn't let you overstate how much you know about the problem. Let's look at another problem that involves the same kind of information. Lawn sprinklers. A lawn sprinkler sprays water 5 feet in every direction. We'd like to know what area of lawn is covered. There's the information we're given, 5 feet in every direction. Well, that pretty much describes a circle, and we'd like to know what the area of that circle is. We'll summarize the information, 5 feet in every direction. That's a circle with a radius of 5 feet, and we'd like to know the area of the lawn. The area is equal to pi r squared. That's 3.14, what we need to remember for pi, times 5 feet. And when we do the math, 5 feet squared is 25 square feet. We report this as 78.5 square feet.